Now, next slide for this is surface tension on a liquid droplet and bubbles. Am I audible to you all? Okay. Next slide is about surface tension on liquid droplet and bubbles. What is the reason why that raindrop, when it falls, it forms a circular shape? That is only because of surface tension, right? So you may have observed that rain that is falling is having a circular shape. That circular particular shape is because of this surface tension that is acting on the surface of the liquid, and it falls, is attracted towards the center, and so that such that the surface becomes round. Now let us talk about different types of forces and related to this droplets and bubbles that are round in shape. Surface tension on liquid droplet and bubble. Consider a small spherical droplet of liquid of radius r. This is half of droplet and half of a bubble. The things that are going is of things that are to be observed are, it is having one surface only, this one, and this is the droplet, and this is bubble. It has two surfaces, one inner surface and one outer surface. Now consider a small spherical droplet of liquid of radius r. One on the entire surface of the droplet, and tensile force due to tension will be, because of this is a spherical ball, there will be a tensile force that is acting on the surface of this droplet. That sigma is equal to surface tension of the liquid. Now let us talk about this is a liquid droplet. It can be water, it can be of different liquids, right? The delta P is the pressure intensity inside the droplet. There is a pressure that is because of which it may burst. Just like if you keep on blowing air inside a balloon, the pressure inside that air is increasing. Ultimately, it has to drop. It will make uh, broke, or that balloon will get torn away. Okay? Now, R is the radius of the droplet. So pressure inside the droplet is delta P. Sigma is the surface tension of the liquid. Let the droplet is cut into two halves. The force acting on one half, the left half will be. Now there are two halves of a bubble. We cut that liquid into two halves, and just considering the left hand side of that half. Now tensile force due to surface tension acting around the circumference of the cut portion as shown, and this is equal to sigma into circumference. Now sigma is acting on the surface of this liquid. The surface of this circumference of this water droplet is equal to 2 pi r. You all know the circumference of a circle. Then sigma into 2 pi r is the tensile force due to surface tension. The force that is acting because of surface tension is equal to sigma into 2 pi r. Similarly, there is a pressure force from inside that is acting towards outside, जिसकी वजह से वो टूट सकता है, हम बिखर सकता है. The pressure force on the area pi by 4 d square is equal to delta P. Delta P is the pressure that is acting inside, and pi r square is this area of this surface that is acting in this. Now these two forces should be parallel or equal. Then only that droplet will become stable. Otherwise that droplet will break away. जैसे हमारा balloon फटता है वैसे ही droplet फट जाएगा. So it will not be stable in that particular. If sigma 2 pi r, that is tensile force that is acting from outside, and pressure force that is acting from inside, if both these forces are equal, then only that water droplet will be stable. Otherwise that water droplet will break away और वो पानी बिखर जाएगा. Now these two forces will be equal and opposite under equilibrium condition, right? So 2 pi r into sigma, that is the surface tension force, and pi r square and delta P droplet. Now this particular equation, 2 pi r sigma is equal to pi r square delta P droplet. These should be equal, right? Now if you bring by pi r square below this, now delta P is this P1, P inside and P outside, change in pressure. Outside pressure and inside pressure. Inside pressure should be higher than the outside pressure. Pi minus P naught, that is outside pressure. Inside pressure minus outside pressure that is equal to change in pressure, that is equal to 2 sigma s by r. Now, if you divide 2 pi r by pi by pi, and r by r, you will get this 2 sigma s by r. This is the equation for droplet. Similarly, if you are talking about bubble, now this bubble, instead of 2 pi r, it is 2 twice of 2 pi r. Now, there are two surfaces, one inner surface and one outer surface. The bubble is having two surfaces. It is empty from inside, right? There will be an inner surface and outer surface. So there will be two circumferences twice into 2 pi r into sigma s, and the inner pressure is pi r squared delta pv, the pressure inside the bubble, and these two pressures should be equal. When you talk about this, from this equation, the tensile force due to in a this is for water bubbles, should multiply it by 2 because of two surfaces. It will become 4 into sigma pi r square, sigma pi r, right? And similarly, this pi r square into delta p is the pressure inside. Now comparing these two, twice of 2 pi r sigma s and pi r square delta p bubble. Delta p bubble is p pressure inside minus pressure outside. If you divide these two, 4 pi r divided by pi r square, you are left with 4 sigma s by r. This is the equation for bubble, right? Now, a hollow bubble like soap bubble in air has two surfaces in contact with air, one inside and other outside. Thus, two surfaces are subject to surface tension. Now, if you have, I hope all of you have done this. I'm going to share the slide, next slide also. Now, next part of this slide is capillarity. We are done with surface tension. Surface tension, what about bubble, about this water droplet, and on numerical on water droplet also. You can even try for numericals on bubbles and all. Now, capillarity. What is capillarity? It is defined as a phenomenon of rise or fall of liquid surface in a small tube relative or adjacent general level of liquid when tube is held vertical in the liquid. If you can observe when you're adding or inserting small tube of small diameter inside some liquid, there will be a rise or fall of liquids in that particular capillary. Capillary is a tube which is having a very small diameter. Rise of liquid surface is known as capillarity rise, while the fall of liquid surface is known as capillary depression. So that liquid may rise in your capillary tube and it may fall in your capillary. This occurs because of forces of attraction between the walls of the tube and liquid molecule. To strong enough to overcome the mutual force of attraction because of molecules or cohesive force. There are two types of forces that are existing in a particular liquid. One is adhesive forces and the other one is cohesive forces. The surface tension is because of cohesive forces. When you talk about this adhesive forces, this is prominent in case of capillary rise. When adhesive forces are more than the cohesive forces, then there will be a rise in liquid level in the capillary tube or fall in the liquid level in capillary tube. It is expression. It is expressed in terms of centimeters or mm of liquid. Its value depends upon the specific weight of the. Generally, how much the rise is taking place in a particular tube is measured in centimeters or mm, and it depends on the diameter of the tube and surface tension of the liquid. Now let us see this diagram that is on your screen. We are having a liquid that is rising in some tube because of this more adhesive forces, right? Adhesive forces are more instead of the surface tension. Surface tension pushes the liquid inside, and adhesive forces rushes or pushes the water or liquid in some small diameter pipe. Consider a glass tube of small diameter, small d, opened at both ends. It is opened from both ends and is inserted in a liquid, say water. The liquid will rise in the tube above the level of the liquid. This is the general level of the liquid. When a capillary tube is inserted in this container or this liquid container, there will be a rise in this liquid. Let h is the height of the liquid in the tube under stable condition. Now, once you have inserted a tube, that water will keep on rising, rising, and rising. But it is not like that. It will keep on rising to up to some say 500 meters and meters. It will get stable at some height. After that, it will not move up. After some time, it will get stabilized, and after that, it will not rise up. Under state of equilibrium, that is, equilibrium state is when there is no movement of liquid in up or down movement. There is no movement of this liquid in capillary, either on upper side or on the lower side. Under the state of equilibrium, the weight of the liquid of the height h is balanced by the force at the surface of liquid in the tube. This weight and attraction, this force of this adhesive forces, these two balances each other at this end, and it is stabilized at this point. But the forces at the surface of the liquid in the tube is due to surface tension. Now this is pushing it downwards. This is pushing it downwards, and there is a rise in the liquid, and there is a weight. Because of this weight, it is also being pushed downwards. Because of surface tension, it is pushed outwards. This because of weight, it is pushing downwards. These two forces should be equal. Now let sigma is the surface tension of the liquid, and theta is the angle of contact between the liquid and the glass tube. Now, what is the angle, theta angle? This is the angle that is we are talking about. Generally, that when the liquid rises in a capillary tube, it is this the surface is never a straight line. It is a curved form. It is in the curved form, right? And this is called meniscus. This is called meniscus. This is called meniscus. And if you draw a tangent from this surface, there will be a theta angle with the tube. That theta angle we are talking about. This sigma is the surface tension of the liquid, surface tension of this particular liquid, and theta is this angle. The weight of the liquid of the height h in the tube. Now, water or liquid that is being rushing out of this tube, that is reach this height. The weight of this particular liquid that is in the capillary tube up to this height, that is taken as W. And that W is equal to area of the tube. Area of the tube. Area of this tube. This is having twice of our radius. That is equal to diameter. Diameter is equal to twice of r into pi r square. Twice of pi r square. So pi by 4 d square into h. H is the height up to which that liquid has risen, and rho is its density, and g is gravity. This is the weight of the liquid that is above this surface of the liquid, right? Now it is being balanced. This weight is being balanced by the surface tension that is acting on this end. This force is pushing it downwards, and this it is being pushed. Because of this force, it is being pushed in the tube above the surface. Now vertical component of the surface tension force. Now sigma into circumference into cos theta. Why we have taken cos theta? Now this is acting in this direction, it has to take two components. One is cos component, 2 pi r sigma is cos, this one vertical component, and one horizontal component. The force that is pushing it downwards, that is vertical, this one, vertical force, that will push it downwards, and or it will act in this weight is acting downwards, and this force that is being acting because of this surface tension from below, that is in the upper side. Then these two forces, if they are normal to each other, that is perpendicular to each other, then they will uh, get balanced. So we are taking cos component over here, sigma into circumference into cos theta. Now circumference is this 2 pi pi r pi d, so pi d is the circumference of this tube, sigma into pi d into 2 this uh, cos component of this, and this is equal to sigma pi d into cos theta. Now pi d can be converted into twice of r, and you can write it sigma pi d cos theta, and height can be calculated, height up to which that liquid is rising in this capillary tube, h is equal to sigma into pi d into cos theta by pi by 4 d square into rho g is equal to, you can calculate this. Anybody who is talking, please, you can ask me question if you want to ask. If there is some problem up to this, I'm going to explain this article again in evening session again, because I have to do it on board also, because I think it needs some clarification regarding the components. So I'm going to repeat that this article again in the evening lecture. So stay tuned with that. Now I'm going to explain you the next slide also. The value of theta between water and clean glass tube is approximately equal to 0. Hence cos theta is equal to unity. Then the rise of water is given by that. If theta is equal to 0, then h becomes 4 sigma by rho g d. This is not the actual condition. Actually, there is some angle also. Now contact angle depends on both liquid and the solid. Rajvinder, your mic is on. Please turn off your mic, or so if theta is less than 90 degrees, the liquid is said to be wet the solid. However, if theta is greater than 90, the liquid is repelled by the solid. Now see if it is like this, meniscus is like this, it is curved, the curve is in the depression at the bottom, and it is rising on the edges. It is called wetting liquid. And if the reverse is this, the curve is like in this direction, it is non-wetting liquid, or we call it repellent. Liquid is repellent by the solid, right? For example, water wets glass but not wets. Mercury, on the other hand, does not wet glass. So this is about this. Now